Hello and welcome. Differentiation under the integral sign for today. Today we have an integral which is rather lengthy in its computation, so I chose to actually do it on my mini board here rather than standing up on the board for a lengthy amount of time. So what do we do for something like that? We have done quite a few of these by now. So first of all, what we need to do is perhaps rewrite this as perhaps, I don't know, let's write it in index notation, x to the half minus 1 all squared, and let's separate the square that we're having in there into top and bottom separately. So I'm going to look at this particular integral, and of course the rationale for something like that is looking at this log of x all squared on the denominator. I know if I introduce a parameter t for the half in there, and I differentiate x to the t with respect to t, of course this will produce exponential coming back, and then I got a log of x, and this log of x should cancel this log x from the denominator. I got it squared, which clearly indicates I might have to do this operation, of course, twice. Okay, so the first thing that I'm going to do is I'm going to define an integral. Let me just write it in a different color. And the integral, I'm going to call it I of t. And the I of t is the integral from 0 to 1, x to the t minus 1 all squared over the log of x all squared dx. Okay, and of course I'm going to differentiate with respect to t and set my plan in motion, and let's see what's going to happen. Okay, so first of all, differentiating now d.I. by dt is of course d by dt of this particular integral 0 to 1, and I've got there x to the t minus 1 all squared over the log of x all squared dx. By Leibniz rule, since I got constant limits in there, I can actually move this differential operator now inside the integral. So if I move it from here and it goes inside, of course, it should really be partial, but it doesn't really matter. You can leave it sloppily as a normal operator. So that's d by dt of this particular quantity. Okay. Let's note now in this particular line, the log of x all squared is independent of the differentiation with respect to t. So perhaps we can, so we have less messy stuff, we can write it as 1 over the log of x all squared. That's this bit here. And then differentiation with respect to t, this particular bracket, we got a simple chain rule. So it's going to be 2 coming to the front. We have an x to the t minus 1 to the power of 1, and then times the differential of this argument, and this of course is going to be x to the t times the log of x, everything to be integrated with respect to x. Of course, let's gonna do a bit of a tidy now. Log of x goes there, and it will go from the square there as well. We got this 2. Let's move it outside for the time being, so we're clearing some of this stuff. 0 to 1. So the 2 has gone. We still got a log of x on the denominator, so let's write it. Log of x, the integral is with respect to x still. And what do we have? We have this bracket times this x to the t, so that's going to be x to the 2t minus x to the t, all with respect to x. So that's my di by dt. Okay, let's write that somewhere, because of course we're going to need it at some stage, so I have it for reference. I need to keep clearing the board, so I do apologize. We need to be very sensible with the use of space today. di by dt, this bit here, is equal to 2 lots, integral 0 to 1, and is x to the 2t minus x to the t, the whole thing over the log of x dx. Okay, so far the plan seems to be working as we originally thought. We are actually clearing the log of x from the denominator. We go and we're gonna have to do it once more now, So unfortunately, we're going to go into second differential. So that's what makes this particular integral a little bit long to compute. We got a lot of work because we have two differentiations under the integral sign in succession. And then, of course, we have to reverse them as per usual. So my next line, we're differentiating again. So we're taking this quantity and we're differentiating with respect to t once more. So d squared I by dt squared is of course equal to 2 lots of d by dt of this integral 0 to 1 x to the 2t minus x to the t divided by the log of x dx. And then again by Leibniz rule, integral rule, we can move this differential now inside. We can swap integration and differentiation. Partial once it goes in, because this will be a function of two variables. So this is brackets there. We'll lose it from the front, but we still got that 2, which we must not forget. And this differentiation now is simpler than the first one. We got the 2 at the front. And actually, it's not simpler. We got a lot of this 2t. So okay, let's deal with it. So we're having, this is the log of x. This will not be in any shape or form affected because of course this differentiation with respect to t as a log of x, and we're differentiating that will differentiate to leave the exponential alone. So because it's an exponential, because of course the differentiation with respect to t times the log of x. But we have a little chain from differentiating the 2t, so we've got an extra 2 in there. And then we got minus, that's meant to be a t in there. We're differentiating x to the t, we just done it a second ago, so it's going to be, of course, x to the t times the log of x integrated with respect to x. And of course, this will simplify. Log x, log x, log x can go. So we have the 2 at the front, 0 to 1. And what do we have left now? We have a 2x to the 2t minus x to the t dx. Is this integral easy to do, is the next question. The answer is very easy, because don't forget now this integration with respect to x. So still the second derivative of y with respect to t is going to be equal to, let's actually move that 2 inside the integral because it's actually easier. It makes no difference to have extra brackets there, and there's a 2 at the front in there. So this now is just evaluation. Increase the power by 1, so that is 2t plus 1, 4 divided by 2t plus 1, minus increase the power by 1, x to the t plus 1, and then the 2 needs to be divided by a t plus 1 with the limits 0 to 1. And remember, we next limits this integration as with respect to x. So it's the x that we substitute in the 1 and the 0. When we're substituting in there, x is equal to 1. This will be just 1. So we're going to get 4 over 2t plus 1 minus 1 again for this, minus 2 over t plus 1. And of course, when we're substituting x is equal to 0, goodbye, goodbye. So there's nothing else but that. We don't even need brackets. So what is sensible to do is actually to clear all of this and move it so I have it next to the second differential up here. So you have to be careful I don't rub off by mistake anything that I might need. So I hope you followed so far what I've done. It shouldn't be too difficult to follow. So the second derivative of I with respect to t is going to be equal to 4 over 2t plus 1 minus 2 over t plus 1. And now we begin the reversing process, the inverting process, or if you want, just going back in our steps, trying to obtain our I of t, because at the moment, of course, we don't have our integral. Okay, we have the second derivative of our integral with respect to t. Is this integration difficult to do? Well, if we integrate back once with respect to t, so I'm going to get, of course, di by dt now when I integrate back. These are just simple logs, so it's going to be let's say 4, so it's a 2 log. I'm not going to put mods because eventually the variable that I'm going to put, the parameter t that I'm going to put there is a half, so it doesn't really matter. That will be positive. You can put mods if you want. 2 log t plus 1 minus 2 log of t plus 1, but let's not forget we got a constant plus c. Okay, we need to evaluate this constant. So we need to look at this line here in purple and put in there a suitable value for my t, which will allow me to work out my constant. So my constant can be evaluated easily if I put t is equal to 0. Because if I put t is equal to 0, my di by dt, which is this, will become, of course, 0, because I'm going to get x to the 0, which is 1, minus x to the 0, which is also 1. 1 minus 1 is 0. The whole integrand is 0. So I'm going to get di by dt is equal to 0, is equal to 2 log, I'm putting t is equal to 0, log 1, which is 0, minus 2 log 1 again, which again, it will be 0. And therefore, this constant turns out to be 0. So that's rather nice because, of course, I now know that my di by dt is just simply the expression that I've got there, and this, of course, is not there. So far, so good. I need to, of course, go back one step so I can get my I of t. All right. Where will I go now with this? Let me just write that on the side. I have just not a very nice integration actually to do there. I don't know if you can see what's going to happen in there. Let me just rewrite this to create a little bit more room, because at the moment it's in an annoying place in the middle of the board. So di by dt is 2 log 2t plus 1 minus 2 times the log of t plus 1. Okay. And of course, I need to go back. So I need to integrate this expression with respect to t, so I can get my I of t. So my I now will be, of course, actually let's write it here. My I is going to be the integral of 2 log 2t plus 1 minus 2 the log of t plus 1. And of course, this needs to be integrated with respect to t. I know how to integrate log of x. I'm going to write it perhaps somewhere at the bottom here. The integral of the log of x dx, it can be done by parts, of course. If you don't know the standard result for that, you can write it as 1 times the log of x. Is actually it integrates to x log x minus x. It's a well-known result, okay, plus some constant. Okay, I would like to use it in there, but unfortunately I don't have an x. I have other bits, which are not that difficult. Perhaps I could attempt it. I'm a little bit tired at the moment. I don't want to risk it because I might make a mistake. The mistake that I might make there is just a factor of 2 or something silly like that. So what I will do is I will use separate substitutions for each of these. So I'm going to say u is 2t plus 1 for this lump here, and v is equal to t plus 1 for this lump here. Technically speaking, and I don't want you to be upset because I'm writing things in a sloppy way perhaps in here, I'm going to split this integral. I don't like to write it like this because it looks a bit bizarre. So I'm going to write this is equal to, put the dt here, so that's the end of this integral. Okay, and of course then we're going to have minus integral 2 log of t plus 1 dt. So that's the other integral, and this substitution is for that and this is for that. That's a lot better. Okay, let's get our bits and bobs. We have du is equal to 2 dt. So my dt that I'm trying to change is du over 2. Well, for this particular one, it's a straight swap. dv is the same as dt. All right, so if I do that, what is going to happen? I'm going to get, of course, my I is equal to the integral 2 log u, that's 2 log u du over 2, and the 2's, of course, will cancel there, minus the integral of 2 log v and the dt will become, of course, a dv. And these integrations now, I have to be careful I don't make mistakes. I'm going to use this result is in x. Of course, here is in u, here is in v. So my I will be equal to x log x minus x. So this will be u log u minus u. Okay, that's for this particular one. This we have to be careful because we've got a minus and we've also got this 2 there. So I'm going to write it like this, 2. And I'm going to put now, I'm integrating log of v. So it's going to be v log v minus v. And of course, plus some kind of constant. I used c earlier on, so I shouldn't really use c again. Let's call it plus d. All right. Let's write it back in t. So my I of t is going to be u is 2t plus 1, very, very messy, log 2t plus 1, so that's this bit here, minus bracket 2t plus 1 minus, I'm going to do a couple of things at once. So I'm going to multiply the bracket and put my substitutions, minus 2v, v is t plus 1, log of t plus 1. So that's that. And then I go plus 2v plus 2, v, and v is t plus 1, plus a constant d. And again, another bit of a tidy. I of t here, 2t plus 1. There's a few cancellations, a few things that I'm going to dump all together into the constant. So I'm getting, if we look at this particular bracket, minus 2t from this bracket here, plus 2t cancel, okay? The minus 1 is a constant. I'm going to put it to d and relabel it. So this I can just throw away altogether. And then I've got, of course, this term here, minus 2 bracket, t plus 1 log of t plus 1. So that's this bit here. So I got that, minus that. This cancelled already. That was the minus 2t plus 2t. I got another number there, plus 2, just a constant. So I'm going to just shove all these bits, dump them into into d and call it e. So this is now an expression that I have for my I of t, for this quantity here. All I need to do is work out this constant now. So let's make some room. Do I have enough room actually to just do it there? I hope it's visible on the video. That's the thing that will annoy me if you can't see what I'm doing. So I of t, which is that, is equal to this expression, but this constant. So I need to put a suitable value for my t in there in order to work out this e. Again, if we look at t is equal to 0, will work nicely, because if I put t is equal to 0, I'm going to get 1 to the 0, which is 1. 1 minus 1 is 0. The whole integrand is 0. So my I of t, if I put t is equal to 0, becomes 0. And what do I get in there? I'm going to get 1 for this bit here. When I put t 0, log of 1, which I'm going to write and cross it out, minus 2 logs of 1 again, which is 0 plus e. So in fact, my constant e is 0. So I'm practically done now. Okay, so let's make some room. I must not lose this line here. So for the final evaluation of my integral, I think in my book I have it as a show, and I think I didn't actually take the show down, but I will know what show I would have put for that. Oops, did I rub it off there? Gosh, I'm talking and I've just lost part of the integral. I think it was a 2t plus 1 there, and that was my I of t. Okay, so let's write it up here before I lose it all together and have to restart from the beginning. So I of t is equal to, I of t first of all is this integral here, is the integral from 0 to 1, x to the t minus 1, all squared divided by the log of x, all squared, dx, and it turned out that it was 2t plus 1, the log of 2t plus 1, minus 2 lots of t plus 1 log of t plus 1. Of course, the plus c vanishes because it was equal to 0. So, okay, what do I get now for this particular integral that I'm after? Because of course this was a construction, temporary construction, in order to do my differentiation and the integral sign. So my integral can be obtained when I put t is equal to a half. So this will now become the integral from 0 to 1 of the square root of x minus 1 over the log of x all squared dx half. So that's going to be 2 times a half, which is 1, plus 1, which is 2, times the log of 2 minus 2. I'm putting a half in there. So that is 3 over 2, 3 over 2. So let's write it straight away to a 3. So that is a 3 over 2 times 2 minus 3 log of 3 over 2. And I know how I would have written the answer. This is good enough, I suppose. That's the answer in exact form. But I wrote it in terms of log 3s and log 2s, and it's just an A-level manipulation from there onwards. 2 log 2 minus 3 lots of the log of 3 minus the log of 2. And then if we collect, I think, log 2s and log 3s, I'm going to get in there a 3 log 2 from this bit here. So I got a 5 log 2 minus 3 log 3. I think that's the answer, the simplest I can actually write it. This was not actually that difficult. All I think this about this particular integral, it was a little bit long. It had this double kind of application of the differentiation under the integral sign, and then we had to integrate these logs, which was just a nightmare. I hope you all followed it, and I'll see you very, very soon. I'm signing out.